Hello, this is Stat134, Lecture 10. Last time we started section 3.1, where I hope to convince you that random variables are great. The reason that random variables are great is because they provide an efficient way to describe an event. So for example, if your experiment is to flip a coin 3 times and x is the number of heads, you can write x equals 1 to mean the event that you have HTT or THT or TTH. In other words, it's a much more concise way to represent an event. As well, it's convenient. Sometimes your random variable has a distribution that's a named distribution, like a binomial or a hypergeometric. So you can just say that x belongs to that distribution. We can combine for example, 3 random variables to make a joint distribution, x, y, z, where we can concisely write what independence means using random variables. And this just means that the cell in the 3-dimensional table of the joint distribution for x is x, y is y, and z is z comes from the product of the 3 marginal probabilities. So we also showed that the sum of independent binomials with the same p is binomial. So for example, if x is binomial n1p, x2 is binomial n2p, x3 is binomial n3p, and they're all independent, then their sum is binomial n1 plus n2 plus n3p. So this is because, for example, if x1 is the number of heads in 100 tosses of a p coin, and x2 is binomial is the number of heads for another 100, and x3 is the number of heads for another 100, all with the same coin, then x1 plus x2 plus x3 is the number of heads for all 300 coin flips. So it makes sense that it's binomial with the same p. And notice here that expectation, which is basically the average, for x1, x2, and x3 is the same as expectation of x1 plus expectation of x2 plus expectation of x3. Now today we're going to show that the sum of independent Poissons is Poisson, as well as talk about expectation of random variables. So to discuss sum of independent Poissons, we recall the binomial theorem, as well as the distribution, the formula for Poisson. I don't have anything to say here. And here's a claim that if x is Poisson mu and y is Poisson lambda and they're independent, then their sum is Poisson mu plus lambda. So how would you show something like this? Well, what you need to do is you need to show that the probability that S is a particular value follows this formula right over here, right? So it needs to follow this formula, and that's what I've done in this proof. So I want you to go line by line through here, and everything should be clear. So next we come to expectation. So the expectation of a random variable is its center. So you can, for example, make a histogram of a list, and the expectation is the weighted average of the values in that list. So for example, the values of the first list here is 1, 2, and 3, with weights 1/4, 1/2, and 1/4, which gives me the average or the expectation of 2, which is the balancing point of the histogram. So now properties of expectation are that the expectation of a constant is the constant. You could just imagine the histogram of a list where it's all just 2. There's just one value, so that would be you'd have a big bar at 2, and so clearly the center of that histogram would be 2. The expectation of x plus y is the expectation of x plus the expectation of y. We saw that with the binomial, but actually you don't even need x and y to be independent. It's true in general. That's something we'll prove another time. And also the expectation of some linear thing like ax plus b, you can write in the way shown. So now when you're computing expectation for complex situations, in particular when your random variable is a count, indicators are a great tool. So that's what we're going to talk about for the rest of the time. So an indicator, it's a random variable that has only two values, 1 with probability p and 0 with probability 1 minus p. So here I've written I, and the expectation of I is 1 times p plus 0 times 1 minus p, in other words, p. So the expectation of an indicator is just the probability that that indicator is 1. That's an important property. So let's look at some examples. So if x is binomial np, so x is the number of successes in n Bernoulli p trials, I'll write x as a sum of n indicators, and here ij is 1 if the jth trial is a success. And so to find the expectation of x, we merely need to find the expectation for each of the indicators, and they're all p, so we get n times p. And notice that these indicators are independent since the trials are independent. Now if we take a hypergeometric, now for example x is the number of aces in a poker hand from a deck of cards. So the values here of x would be 0, 1, 2, 3, or 4, because we only have 4 aces in a deck. And so n here is 52, g is 4, n is 5. We want to find the expectation, so we write it as a sum of indicators, where ij is 1 if the jth card is an ace. Now the jth card being an ace is an unconditional probability. So the probability is g over n, and that's the same for any j. So the expectation of x then is n times g over n. Now the important subtlety here is that these indicators are dependent on one another because we're drawing from this deck without replacement. However, these indicators, the probability that they're 1 is an unconditional probability that doesn't depend on any of the other cards. So let's take a look at an example. Suppose a fair die is rolled 10 times. Find the expected number of different faces that appear in 10 rolls. So for example, if your 10 rolls results in a 2, 3, 4, 2, 3, 5, 2, 3, 3, 2, we have x equals 4 different faces, namely 2, 3, 4, and 5 are the different faces. So the step in answering the question is to write what x is and find its range of values, write x as a sum of indicators, and then find the probability that that an indicator is 1. Okay, so x is the number of different faces in 10 rolls. So when I say different faces, I mean the number of faces that appear at least once in 10 rolls. So for example, the possible values for x is 1, 2, 3, 4, 5, and 6. So when x is 4, an example of that would be what I gave, the result of 10 rolls that I gave earlier. So most of you got this wrong when you were trying to do this in class, but the correct way to proceed is to write x as a sum of 1 through 6, where ij is 1 if the jth face appears. In other words, I1 is 1 if 0 appears at least once. I'm sorry, if 1 appears at least once. I2 is 1 if the face 2 appears once in the 10 roles. I3 is 1 if the face 3 appears at least once in the 10 roles, and so on. So you can see here that this is going to get what you need, and the probability that ij is 1, in other words, that you get the jth face at least once, is 1 minus the probability that the jth face never appears. So for example, if it's face with a 1 on the top, the chance that that never appears is 1 minus 5/6 to the 10th power, because it would mean that I'm getting something other than a 1 for each of the 10 rolls, and there's 5 out of 6 chance of that, each independent, so to the 10th, and then 1 minus that. So we get that our expectation is 6 times that probability. So then I gave you this concept test. A forgetful valet is attempting to return n cars to their n rightful owners. For each driver, the valet remembers the car correctly 5% of the time. Otherwise, the valet retrieves a car at random, possibly the correct car. Let n be the number of drivers who retrieve their own car, and I asked you to find the expectation of n. So the correct answer is B. So let's see why here. So n is the number of drivers who retrieve their own car, and so that's a number between 0 and n. So quite naturally, we'll write n as the sum of n indicators, where ij is a 1 if the jth driver retrieves their own car. And let's say that that has probability p that we need to find. But I want to mention that these indicators are dependent. So most clearly, if the first n minus 1 drivers retrieve their own car, then necessarily the last nth driver must retrieve their own car, right? Because there's only 1 car left. So there's clearly a relationship between these indicators. So, and then furthermore, I want to indicate that the probability P here, that the jth driver retrieves their own car, is an unconditional probability. So this should be the same P for all j, 1 through n. So let's find what that P is. So by the addition rule, the probability that the jth driver retrieves their own car is the probability that the valet remembers, plus the probability that the valet forgets and chooses correctly by the addition rule. So the probability that the valet remembers is 0.05, and the probability that the valet forgets and chooses correctly by the multiplication rule is the probability that, given that they forget, that they choose correctly, times the probability that they forget. So that's 1 over n times 0.95, giving you the expectation of n is n times 0.05 plus 0.95 over n. Anyway, that's how it goes, and lots for you to think about on this week.